Okay, that was kind of fun, but my wife's sitting over here laughing at me, so I think it's time to turn on the lights and get back to the chemistry. Nerd. All right. Well, folks, when we were, let's see, if I move my head just right, it's kind of like I've got a halo behind me. Can you see my halo, halo, halo? Okay, well, anyway, last time when we were talking, we talked about solution phase peptide synthesis. And we talked about how it's a good method using protecting groups to govern which amide bonds are formed when between amino acids. But we mentioned that it suffers from some challenges. First, it's limited in how long you can make your peptide because yield drops off with each additional step. And second, you've got a purification problem, which increases as the peptide gets longer, because you have to hope that the product of your peptide, or rather the product of your coupling reaction, differs enough from the starting materials that you can easily separate them. And a potential solution to this was invented in the 60s by Professor Merrifield at the Rockefeller Institute in New York. And Professor Merrifield went on to win the Nobel Prize for this technology. So it's important. It's one that we still use today in my lab, and it's one that can allow us to access peptides up to 60, or maybe if you're pushing it, even 100 amino acids in length. So with that, we'll switch to notability. And your text calls this method the Merrifield method, after Bruce Merrifield. But more broadly today, it is called solid phase peptide synthesis. And just to introduce the idea, let's imagine that you were trying to couple two amino acids together. Let's suppose you were trying to couple a valine with, let's say, a proline. One, two, three, no, sorry, got the size of the ring wrong. 1, 2, 3, 4, all right. And suppose you did this coupling reaction using DCC, and let's see, I need to move this over to make myself a little bit more space. So your desired product would be the dipeptide with valine at the N terminus, and then proline at the C terminus. Like this. And suppose the yield wasn't very good. Sometimes beta-branched amino acids don't couple on very well because of steric hindrance associated with the large side chain. Couplings with proline can be difficult because the proline secondary amine is somewhat hindered. So suppose you did this reaction and the yield wasn't very good. One of the things you might do to try to increase the yield might be to add excess equivalents of one amino acid relative to the other. For example, if a one-to-one mixture of the valine and the proline gave you let's say 50% yield. What if you tried a 5-to-1 mixture of valine to proline and used used one equivalent of DCC for every equivalent of valine? You'd have an excess of amino acid, you'd have an excess of coupling reagent, and hopefully that would push the reaction to completion. But if you use an excess of one amino acid relative to the other, you suddenly have a purification problem, because now you have to separate your desired dipeptide from the unreacted 4 equivalents of valine. And this is a problem. As we've talked about before. So you're sort of stuck because you'd like to increase the yield, but anything you might do to increase the yield in solution phase synthesis would naturally make purification even worse. So Merrifield had a really interesting idea. And his idea was, what if we covalently attach one amino acid to a large polymer? In fact, let's have this polymer be large enough that we can manipulate the polymer, move it around. Perhaps it could be a small bead. And if we attach the amino acid through a covalent bond to that polymer, could we then start doing coupling reactions that would attach additional amino acids to that polymer? Now, the usefulness of this method may not be immediately apparent, so let's set it up a little bit. The polymer that Professor Merrifield worked with was polystyrene. And actually, I have some experience with polystyrene. We've been playing with polystyrene shrinky dinks at the Price household past couple of days, so I'll just show you some of my work. Let's see. Whoops. This is my shrunken Mandalorian Death Watch symbol. And this is my shrunken polystyrene Mandalorian helmet. I'm trying to figure out which way left is left and right is right. Anyway, shrinky dinks. Who knew? Kind of fun. Good for hours and hours of entertaining even teenagers. Polystyrene is a polymer of the following molecule: benzene ring attached to a double bond. This is styrene. And if you expose styrene to a radical initiator, you can start a polymerization reaction. So let's see. Yep. Oops. There we go. You can start a polymerization reaction where the radical attacks the pi bond to make a new sigma bond. And then you've got a new radical intermediate where you've got the radical on the benzylic carbon where it's stabilized by resonance with the phenyl group of the benzene ring. And then that resonance stabilized radical can go on to react with another equivalent of styrene, adding another 2-carbon unit to our chain with the radical on the end. And this will happen many, many, many different times until you have basically a long hydrocarbon chain where every other atom along the hydrocarbon chain is a benzene ring. And depending on the conditions, sometimes, I guess I should say this about polymers, because the reaction goes on so many times in this chain reaction to add so many of these styrene subunits to the polymer, the properties of the polymer are actually governed by the styrene portion, and it doesn't even matter really what this end group is in terms of the properties of the polymer. So this would be a linear polystyrene, which is abbreviated PS, a linear polystyrene chain. And over the course of the reaction, sometimes a radical will abstract a hydrogen atom from one of these benzylic carbons, and you'll get a second benzylic radical, and then you can start polymerization off one of those benzylic carbons again. And so that starts to result in cross-linked polymer. And depending on how you do the polymerization, so here's the benzylic radical, here's an example of the cross-linked polymer. Oops. We're kind of running out of space here, folks. I'm sorry. So here's an example. You'd make a new bond there. Here would be the new radical, and then additional molecules of styrene would get attached. Oops. Looks like I did it wrong. Sorry, folks. And so on. And you can have several cross-links at various carbons. And of course, the more of the cross-links you have, the more rigid the polymer might be. And if you get enough of them at certain temperatures, the polymer goes from a liquid to a solid. And you, depending on how you run the reaction, you can control the properties of the polymer. With polystyrene, you can heat it up to about 180 degrees and then extrude it through an opening, and you can cast it into sheets. But you can also break it up into small spherical chunks called beads. Now, so far, you've just got polystyrene, right, which is a major component of packing peanuts, those big styrofoam balls that you find at Hobby Lobby that you can use to make your horrendously not to scale elementary school solar system exhibits, giving rise to Brian Regan's bit about how the big yellow one is the sun. So this is polystyrene. Merrifield's innovation was to mix regular styrene with a small amount of chloromethylstyrene, parachloromethylstyrene. So you've still got the place to do polymerization, but on the opposite side of the ring, you basically have an alkyl halide. This is a usable functional group that Merrifield incorporated into his polymer. So if you take these together and you do radical polymerization, and you cast the resulting polymer into such a way that it makes beads, what you can get is this highly cross-linked polymer bead in which some of the phenyl groups, not all, but some, have been replaced with the chloromethyl phenyl groups. So at some interval, and we're not specifying how many of them there are, and you wouldn't have control over where they are, but how many of them are you could control. You could control by how much you mix, by the ratio of chloromethylstyrene to regular styrene. And so you would create this polymer bead that had places within it where you could attach other molecules. So here's some examples. Now, for the purposes of our discussion here on out, I'm going to represent this huge, well, maybe we'll keep it like that for now. So you've got a polystyrene polymer where you've got these good leaving groups at various positions through the polymer. And Merrifield basically asked what would happen if I added some Fmoc-protected amino acid with some side chain, care what the side chain is, and then let's add a small amount of non-nucleophilic base like triethylamine just to remove the proton from the carboxylic acid. Could you then do SN2 type chemistry using the carboxylate of the deprotonated amino acid as a nucleophile and simply do backside attack on the chloromethyl group and attach the amino acid to the polymer? So I'm going to copy and paste because this will take forever. And if you need to pause, if you want to draw in your notes, go ahead and do that. We're just showing the mechanistic step where the SN2 reaction happens. And you would be left at this position with an amino acid attached to the polymer through an ester linkage with a benzyl carbon. Notice how what I'm going to highlight in purple, notice how this portion of the molecule kind of resembles the benzyl ester protecting group we've used previously. Oops, got the stereochemistry wrong. The benzyl ester protecting group we've used previously for keeping the carboxylic acid group from interfering in a reaction. So you're basically using this polymer bead as a protecting group for your carboxylic acid, but the protecting group is something you can actually pick up and see macroscopically. You can scoop it up, you can hold it with a pair of tweezers, and the real genius of this is that as long as you can see the bead, you know where your amino acid is. And so let's draw other equivalents of this amino acid attached to this polymer bead. There we go. Okay, and each bead would presumably have thousands of these spots, thousands to millions of these spots to put amino acid on. And then in a particular sample, you'd have many different beads. I guess at this point we will say that the polystyrene beads are sometimes very small, and we also call them resin. Not sure why. And to simplify our drawing, I'm going to represent this large polystyrene polymer where we functionalize the chloromethyl groups with amino acid. I'm going to represent this as many in the field do, with a big circle, and sometimes we'll put a PS inside the circle so that we know that it's a polystyrene bead. And then I'll put one of the CH2 groups, and then I'll put the amino acid. Okay, and when we look at this drawing of our polystyrene bead, and actually when you make them, they're kind of an orange or sort of yellow color. Not sure that that matters, but we'll color it here. When you see this sort of image, you have to remember that each bead hosts large numbers of amino acid. So usually each bead hosts lots of sites for amino acids to attach. Usually these beads have about 1.0 millimoles of attachment site per gram of resin. Or another way of saying that is to say that each bead has about 1.0 micromoles of attachment sites per milligram of resin. So even if you have a small amount of resin, by lots here, understand we mean something like 10 to the 18 to 10 to the 20 different sites per milligram of resin. So even though we're only showing one amino acid coming off this bead, you have to remember that there's like gazillions of amino acids going attached to this bead. And even though we're drawing it as though the amino acid is attached only on the surface of the bead, remember that it can be anywhere in the bead where there's a chloromethyl group. All right, so what? We've got this big clunky protecting group now on which our amino acid is attached. Who cares? Let's imagine how this might change our peptide synthesis. Okay, suppose we want to attach another amino acid onto the first amino acid that we put on the resin. To do that, we would need to first remove the Fmoc protecting group on this green nitrogen. Okay, so to do that, we could expose the resin-linked amino acid to 95% TFA in water. When you write 95% TFA, usually people assume you mean 5% water. Those are conditions that deprotect Fmoc, but this linkage between resin and amino acid is stable to TFA. So it's going to stay intact. So after you do the Fmoc deprotection, you've now released your amino group. which we can color green. It's now ready to go in the next coupling step. And instead of having to do anything to isolate your deprotected amino acid, you simply have to wash away the solvent and the bead stays behind. Let me give you a sense for how we do these reactions. So imagine you have a reaction vessel that looks something like this. It's just a long tube. At the bottom, you have polypropylene or some kind of filter disc. Oops. And the filter disc lets solvent and small molecules through, but not polystyrene beads. Okay, and at the end of the filter disc you have an outlet, and then you can put a cap let's see, at the end of the filter disc you have an outlet, and then you can, while you're doing reactions, you can put a cap on the outlet to prevent stuff from leaking out. Let's see, here's the filter disc. For fun, let's color it gray. And so instead of using a round bottom flask, what you'll actually do for this reaction is you'll put the small polystyrene beads in this reaction vessel. And then you can add the 95% TFA in water to this reaction vessel. TFA is colorless, but it's highly acidic. I'm not sure what we want to do. Color there probably is way less important than I'm making it out to be. But hey, we like color. So TFA is not green, but we're using green because we're being silly. So you can put the Fmoc Deprotection solution in the reaction vessel, and you can put, if you want, you can put a little stir bar in the reaction vessel and set this thing on a stir plate, stir the resin beads in the reaction vessel. When you are done and you want to get rid of the TFA, get rid of the T-butanol that comes off from the Fmoc protecting group as we talked about last time, all you do is you take this reaction vessel and you put it, you uncap the bottom and you stick that on a vacuum manifold. Usually the vacuum manifold has not going to be able to draw it, but basically some kind of stopcock here that allows you to open the reaction vessel, and then you have some kind of receptacle down here that the solvent can go into once you open that stopcock. So, and then that vessel is itself dang it. I'm not drawing very well. The vessel itself is connected to a vacuum. And this is an oversimplification, but you open the stopcock and then your TFA solution drains out and leaves behind the resin beads. So now your TFA solution is here, your tert-butanol that came off in the Deprotection is there, and you now have these beads of resin that are basically, you've done a purification reaction without having to run a silica column. And then you can also rinse with some solvent that will wash out the residual TFA. Often the solvent we use is dichloromethane. And so you can do that 3 to 5 times. And by the time you're done, there's hardly any TFA at all left in your resin beads. So by simple draining the reaction mixture from the vessel and then rinsing the beads, you've now purified your desired product here, this deprotected amino acid on resin. And so that is what we call a deprotection step. Then we can do what's called a coupling step. And this is where we're going to take our reaction vessel that has this bead in it. We'll put the cap back on. And to this reaction vessel, we're going to add the next amino acid. And we're going to use the amide bond coupling conditions, the same ones we used in solid phase, in solution phase peptide synthesis. That is, we're going to still use DCC as our coupling reagent to make the amide bond. And we're still going to use a Bock protected amino acid. Whatever side chain we want, we can use. The Bock protected amino acids you can either prepare yourself, or what we do now is we usually buy it because you can get them for cheap. But this time, instead of using one equivalent, we can use maybe 5 equivalents of DCC and 5 equivalents of the amino acid. We can use a huge excess. A typical solvent is DMF, which stands for dimethyl formamide, 2 methyl groups on a nitrogen and a proton on the other side. This is a typical solvent for coupling reactions. It is also colorless, but what the heck, let's choose purple. So now you've got your reaction mixture stirring, and this is your coupling solution, 5 equivalents of DCC and 5 equivalents of the carboxylic acid. And you're not doing that because you want 5 additional amino acids attached. Once the single amino acid attaches to our green amino group to form an amide bond, the N-terminus of that dipeptide is blocked by Boc, and so the reaction stops. The deal with using the excess amino acids is to force the reaction to completion. So when this reaction is done, what you have is resin beads where you now have attached a second amino acid to the N-terminal amino group of your first amino acid, and then that nitrogen is Boc protected. So now your green nitrogen's tied up in an amide bond, and your purple nitrogen is Boc protected, and presumably still in your reaction vessel in solution, you still have 4 equivalents of the amino acid and DCC left behind. But no worries, we don't have to do any special kind of purification. We just take the reaction vessel over to the vacuum manifold. I want to shrink that. Doesn't want to shrink. Maybe I should have used Shrinky Dinks. None of you, of course, know Homestar Runner. That was a thing from the early 2000s, though it still exists, and you might want to look it up. There's a character on there that speaks with a Midwestern Minnesota/Wisconsin type accent, and he can't pronounce words very well. His name is Coach Z, and we think he would say Shrinky Dinks. Shrinky Dorks. Silly and dumb, but that's what we laugh at when we're on quarantine. Right, so, oops, didn't want that to happen. So, yeah, we'll remove the cap off of our reaction vessel. We'll open up the stopcock. The purple solution drains out. Now you've got your 4, oops, I guess we can write that with black ink. Now your 4 equivalents, smaller font. Now your 4 excess equivalents of amino acids and DCC and your solvents DMF are all in the bottom of the flask. They've all drained out of your reaction vessel. And what you've got left is your resin beads, which are now, and which you can now rinse 3 to 5 times with dichloromethane. You probably also want to rinse with DMF. By the time you've done that, all of the excess reagents are gone, and you have basically purified your peptide by simple filtration. And so that is a coupling step. All right, so to installing a new amino acid consisted of first doing a deprotection step to remove the Boc group, and second, doing a coupling reaction to put the next amino acid on. And so you can continue through this method. You can take this dipeptide and, oops, didn't want to do that, and continue adding amino acids to it. I suppose now is a good time to mention that because you can use, the Boc deprotection reaction was always great, and that's going to continue to proceed in about 100% yield. But because you're using 5 equivalents of DCC and 5 equivalents of your amino acid, and because the purification is so simple, you're going to get yields that are sort of in the 90 to 99%. And if your yield's going to be around 90 to 99%. You can access much longer peptides than you could if your yields were like 80%. So let's do just a little bit of math. Let's suppose our yield is 90% and we want to make a 30 amino acid peptide. If our yields were 90% and we made a 30 amino acid peptide, per coupling and deprotection step, you would have 4% yield. With solution phase peptide synthesis, we got 0.12% yield, so that's a 42-fold increase in efficiency. If we go to 95% yield per step, we get an overall yield of 20%. And so we can start getting sizable amounts of longer peptides by using this solid phase method. So let me show, and of course if you can get 99% yield at each and every step, you start to be able to have 73% yield by the time you get to a 30 amino acid peptide. So let's show you how we would continue to elongate the peptide. We would do the Fmoc deprotection step. (95% TFA). And then in the second step, we would do the coupling reaction. And this would be 5 equivalents of DCC and 5 equivalents of your Fmoc protected next amino acid. We'll make that amino group blue. And in between the deprotection and coupling step, you would rinse. After the coupling step, you would rinse. Once we complete one cycle of coupling and deprotection, you've now attached a third amino acid to our growing peptide. And now it's just a question of how many amino acids you want to add on with iterative cycles of deprotection, rinse, couple, rinse. And you can make peptides that are 30 or more residues by this method. The method actually is, because it occurs iteratively, it's amenable to automation. And one of the first things the Merrifield Research Group did was build an automated solid phase peptide synthesizer. We call it solid phase because the polystyrene bead is solid. So this pattern of deprotection, rinse, couple, rinse on resin, we're going to call solid phase peptide synthesis, and some people will abbreviate that SPPS. They'll call it, as we've shown you here, Fmoc solid phase peptide synthesis, because we're using the Fmoc protecting group strategy for the nitrogens. So it turns out that the Merrifield group got very good at this. We're going to let's see, look at Merrifield automated peptide synthesis. And maybe we'll be able to see an image of his early work. So here's a picture of Merrifield's peptide synthesizer around 1964. And you can see This portion is electronics to control the flow of solvent. Here are pumps to control which solvent and which reagents go where. Here are the solvent reservoirs. Here is the reaction vessel. There is the stopcock at the bottom. There is the filter disc, and this is where the resin would go. And they built this, and they used it to fascinating effect in, let's see, we need to look up Merrifield ribonuclease A synthesis. Maybe it wasn't A, maybe it was just ribonuclease S. In 1971, just a few short years after developing the method, Professor Merrifield used this method to synthesize subunits that he could bring together to make a larger protein. So I thought we were going to get more data here. Dun, dun, dun. Well, what I mean to say is that in the end, Professor Merrifield was able to do chemical synthesis of a 124 amino acid molecule. And it was the first to show that you could make a protein synthetically, and it would have, enzymatic activity similar to the protein that had been isolated from natural sources. All right. And for this, Merrifield won the Nobel Prize along with others. All right, so that's the basic idea. We should talk about how to remove the peptide from the resin, because you can't keep it there forever, that's silly. So let's just imagine all we wanted to make was a tripeptide, because I don't want to draw a 30 amino acid peptide and you don't want to draw it either, or watch me draw it. It turns out that you can do the way to release the peptide from Merrifield's resin requires hydrofluoric acid, HF. Now, HF isn't a very strong acid, and it's thought that this reaction works basically by an SN2 reaction. Basically, the fluoride is going to come in as a nucleophile and attack here, and the carboxylate will leave and get protonated, probably by the HF. In any case, the reaction HF cleaves this bond between the oxygen and the benzylic carbon, and it releases the peptide. Oh, and I suppose before we cleave it from the resin, we would need to have done the final Fmoc deprotection, so that now we have the N-terminal amino group. Sometimes people want to put other groups on that N-terminal amino group, and they can, but let's suppose we've taken off the N-terminal amino group. We use HF to cleave the peptide from resin, and now what you're left with is your desired tripeptide. So HF does what we call the cleaving reaction. It cleaves peptide from resin. So that would be the last step to liberate your peptide. Now, some of you may know a little bit about HF from chemical safety classes. It's a pretty nasty reagent. You have to have a special hood to deal with it. And if you get it on you, you can die. I'm told that it's not that tricky to deal with as long as you know what you're doing. Never done it myself and never actually really intend to. To avoid having to use HF cleaving conditions, chemists have developed an alternative involving a chemistry involving what's called Fmoc chemistry. So we're getting close to time, but I want to just say a bit about Fmoc chemistry so we can move on to other things in the next lecture. The idea to avoid HF is, let's make a resin with an attachment site that can be cleaved under other conditions. In this case, what if you made a resin, a connection between the resin and the amino acid that was cleavable under acidic conditions? So this now allows us to introduce a linker called the Wang linker, I guess. And this is still a polystyrene resin, but instead of incorporating the parachloromethyl group as the attachment site, let's see. And then you could attach the amino acid to the resin under these, and I'm just going to put protecting group here on the nitrogen. And it turns out that the change in the structure of the linker makes this bond labile or susceptible to 95% TFA. And it's thought that what happens when you put this molecule in TFA, and let's just imagine that we've already made our peptide. We're done with the peptide synthesis. We want the peptide to come off the resin. We add TFA, we protonate the carbonyl oxygen. At that point, the oxygen here leaves from the benzylic group and takes these electrons, and your peptide leaves from the resin. That's the cleaving part of the reaction. But it leaving is aided by the fact that the carbocation that stays behind, so it's sort of an SN1 type cleaving reaction, and the carbocation that stays behind is not a primary carbocation because it is stabilized by resonance with the para oxygen. So we could draw a resonance structure in which we delocalize that positive charge onto the oxygen. And that makes leaving under acidic conditions quite easy. So cleaving from the resin that has the Wang linker attached to it involves protonate the carboxylic acid, protonate the C-terminal carbonyl oxygen, and then SN1 peptide leaves from benzylic carbon to give a resonance stabilized carbocation. So Now, TFA is still a fairly acidic substance, but it's not nearly as dangerous as HF. And we use it all the time in my lab to cleave peptides from resin. The challenge is, now that you're going to use TFA to cleave your peptide from resin, if the attachment to resin is cleavable under acidic conditions, you can't use Fmoc to protect amino groups anymore. Because if you did, anytime you went to deprotect an amino group, you would release your peptide from resin. So chemists needed, there's 3 E's in that needed, that's embarrassing. Well, there's supposed to be 3, there were 4. Chemists needed an amino protecting group that was let's see, that was cleavable under non-acidic conditions. And there was a number of things that were tried, but ultimately chemists settled on what we're going to call a base labile protecting group. That means it's removable under basic conditions. And this protecting group is called Fmoc. We call it Fmoc because nobody wants to say Fmoc. I'll show you what F stands for. F actually stands for an interesting and somewhat strange looking hydrocarbon. You have 2 benzene rings fused to the same 5-membered ring. And interesting enough, that hydrocarbon is called fluorine, not fluorine, the F from our periodic table. For whatever reason, it's called fluorine. And then there's a methyl group on it, or sorry, a CH2 group. The CH2 group is attached to an oxygen. The oxygen is attached to a carbonyl, and then that carbonyl is attached to the amino group of your amino acid. So this is an Fmoc protected amino acid, and people will abbreviate it like this. And you can buy these Fmoc protected amino acids. You'll notice some similarities to the Fmoc protecting group. First of all, pay attention to this embedded CO2 in the backbone, or rather in the structure of the protecting group. Also notice another feature. You've got a proton here adjacent to the oxygen within your protecting group, and you might expect that proton to be somewhat acidic, in the sense that if a base were to remove that proton, we would have a resonance stabilized carbocation. So let's just redraw that Fmoc group, or rather, let's draw the conjugate base of what we just drew with lone pairs here on that carbon. Friends, hopefully you can see how that negative charge could be delocalized on these 3 carbons and on these 3 carbons. And another interesting thing to look at is the number of pi electrons here now involved in this ring system. You've got 6 here, 6 here, and then 14 pi electrons in a conjugated system of rings. That's aromatic. Okay, so that the aromaticity that you get is why that proton in the fluorine group can be removed by a base. Once it's removed by a base, you can do an elimination reaction. We probably would call this an E1CB reaction because you make the conjugate base, and then these electrons kick down and kick off the oxygen as a leaving group, but instead of just kicking off the oxygen, the electrons come here to form a new carbon-oxygen pi bond. That turns the ORG group into CO2. These electrons have to leave. They could go straight on to the nitrogen, but as they're leaving, probably that nitrogen picks up a proton, probably from the conjugate acid of our base. And so what we're left with is the elimination product, which is actually called dibenzofulvene. You don't need to remember that. And it's fluorescent. You also don't need to remember that. You also get CO2 as a byproduct, which bubbles off. And then your amino group is free. So, solid phase peptide synthesis under Fmoc conditions is only slightly different from solid phase synthesis under Bock sorts of conditions. You'll have your amino acid attached to the resin. You can attach that amino acid in exactly the same way as we attached it to the Merrifield resin. And let's assume that we've put that first amino acid on and it is Fmoc protected. We'll use a strong base, and actually the base we're going to use is an organic base. It's a secondary amine. It's called piperidine, and we're going to use a 20% solution of piperidine in dimethylformamide as a solvent. So piperidine is just our base to remove the Fmoc group. This is our deprotection reaction. And then in a second step, we're going to bring in a second Fmoc protected amino acid. We'll bring 5 equivalents of that, 5 equivalents of DCC. That is a, oops, missed a bit. That is a coupling step. And once we've done that, we will have attached, and we're going to do that in exactly the same way as we did above with Bock chemistry. We're going to do the rinsing, stirring, washing of the resin. That will allow us to attach a new amino acid to our green amino group via an amide bond. So here is our new R1 side chain, and then here is the Fmoc protected purple amino group, and we're going to continue on repeating cycles of deprotection and coupling until we get to the very end, and the last step will be one final deprotection step to remove the last Fmoc group. And then we will do 95% TFA to cleave the peptide from resin. What we'll be left with after that is what I showed you here, a resonance, oops, I didn't want to cut, I just wanted to copy, a resonance stabilized carbocation, and of course your peptide, whatever it is. Oops. Sorry, folks, let me try again. You'll end with your peptide removed from resin. And at that point, you can then purify your peptide, usually by high-performance liquid chromatography, and you can characterize it to make sure it's the right thing. This method allows you to prepare a peptide without ever having to see HF. And it works almost as well as the Bock chemistry. It turns out that the piperidine deprotection reactions are not quite as efficient piperidine Fmoc deprotection reactions are not quite as efficient as the TFA-based Bock deprotection conditions. So in practice, with Fmoc chemistry, you're limited to peptides in the 30 amino acid range. Though people in my group are pushing that to be, and actually people do it fairly routinely. You can get to peptide lengths that are much longer now using modern technological developments. But this is how you synthesize peptides. And this Fmoc chemistry is actually the chemistry that was used to prepare the HIV drug Fusion. And the development of that drug and the massive amounts of Fmoc protected amino acids they had to get to build that drug drove the price of Fmoc amino acids down to the point that a lot of people have adopted Fmoc chemistry, and that's the most common way to synthesize peptides now. If you want to learn more, come talk to me about my research. People in my group do this all the time, and it's kind of a blast. But until then, stay safe, stay healthy, and stay organic. That's my dumb sign-off line. Pretty impressive. All right. Have a good night, folks. Talk to you later.